All right, number of good leaf node pairs. This one is a great problem. Uh, it requires some thought to, and there are different approaches. The approach that I'm going to show you, it requires some thought to it in terms of implementation because it is basically backtracking. But this one, it is very intuitive, the one that I'm going to show you. It might not be the most optimal, but it is intuitive. So basically, the question states that you're given a binary tree. It's not stated that it's unique values also, so that will be wrong to assume for us. But what we need to do is basically for each leaf node, we need to find pairs which are at some distance which is lesser than equal to a distance d given in the question. So basically, if this is the binary tree, then this one is a leaf node. We travel here. This is one distance. This is two distance. So two, and this is one distance, three. So three distance. Uh, so this is one pair, right? So if you try to solve this mentally, how are you going to solve this? You see that you can do a DFS from the leaf node and then do and try to reach another leaf node, and you can do the same thing for all the other leaf nodes, and eventually you will get a value, an answer which is double of what is the required answer, because for three also you'll do the same DFS and you will reach four and get an optimal distance which is contributing to the answer. And from 4 also, you'll do a DFS, then you'll get answer is 2, but the answer is 1 because only one pair can be formed. Basically, you're doing 4, 3 and 3, 4 as two separate answers, but by the end, you'll do a divide by 2. Alright, that's one way to solve this. But what I'm going to show you is do a single DFS, but we'll maintain the distance, the depths. Alright, so I'm going to show you in order traversal. So for in order traversal, this is what you're going to do. We are going to come down. Right now, my depths, I'll be having a depth. All right, this will be a vector. All right, right now it's empty. I come here, it's empty. Now I go here, there's nothing, so I return back. I go here, there's nothing, I return back. I see that I'm backtracking, so at this point, the root or the node where I am, is it a leaf node? It is a leaf node. So I add a depth. Probably depth is not the right name to the variable. Something like distance. Distance will be fine. The value with which I'll enter is 0. So I'm at 0 distance. Okay, fine. Now I come back, I come up. The depth or the distance is what? I have only one value because I haven't counted only one leaf node, and it will be 1. Alright, good. I backtrack, I come up, it's still 1. Oh, sorry, my bad, my bad. I completely forgot that we are going up, right? Let me come back to the point where we added the distance. Alright, I added 0. We backtrack. When we do a backtrack, we should increase the depth to 1. Why 1? Because we have traveled one distance. We do again a backtrack. We reach the root node. The distance is now 2. We do a, you know, we go inside of its right node, and the depth is now 3. We see that distance is 3, and the distance that we require is also 3. So it's fine. We can add this pair. So we add this pair. So right now we have depths as vector, right? Or distance as vector, because we can have multiple leaf nodes, and for a particular node, I want all the other leaf nodes distances till this point. Right? Let me show you another example, because we have to do certain things for this to work. This one was not a great example. This one is good, better example. So here we do the same thing. We have a depth, a distance vector. Uh, I come down, I check here, this is leaf node, great. So the current distance will be 1, 2. 2 will be the distance, great. I go up, sorry, not 2, 0 will be the distance. I don't know, I'm out of my mind again, I guess. 0 will be the distance. I backtrack, now 1 is the distance. I come down, at this point there's something happening which we need to take care of, okay. When I'm coming down, the distance should be 2, which is great. But now when I come up, the distance should reduce, right? But this is the same scenario that we might do here as well. The distance should reduce when I go up. But should the distance reduce here? No. I'm coming up here as well. Should the distance reduce here? No, it should increase. So for the same state, I can't really increase or decrease the distance, right? When I have, I just need to keep track when I am going down. I can only reduce. Just think of it like this. Okay, I'll do it again. Probably it's a little confusing, so please pay attention. I'm here, 0. Alright. I go up, distance is 1. I come down, distance is 2. Now I'm going back up, right? So I come down and go back up. So if I come down twice, I can reduce the distance twice only. The third time I'll increase it. This is the third time. So we're basically keeping track of how down we have gone so that we can reduce the distance as we go up till that point itself, till that point alone, not beyond that. So if I've come down, suppose there is another node here, another node here, I go up, I come down, I come down. So I have come down twice. Alright, suppose this is not there, just to make things easier. I come down twice. So if I go up, I'll reduce the distance only twice because I've increased the distance twice when I came down, right? So that's what we are going to do. So how we are going to do that? I can have a vector or a 2 field, a pair. Instead of depth or distance, I'll also have a second pointer which will be a vector. So there's nothing to name it, but I'll call it for the sake of it, I'll call it down. Right? So right now I've gone down 0 since I've only initialized the distance. Let me clean this up. I go up. The distance is what? That's 1, 0. I've not gone down even once, so I've increased it. Increase it if I go up. Increase the distance if I go up. I go down. I increase the distance because it's still 0, but I increase down as well by 1 because I've come down. Now I go up. I reduce back the down pointer, down variable to 0, and I've reduced the distance also by 1. Right? Now if I go up, I see that the down vector, down pointer or down variable is 0. So if I go up, I should increase the distance to 0. Alright, now I go down. This will be 3, 1. I've gone down, right? Alright, clear this up as well. Write it properly. This is 0, 0. This is 2, 1. Sorry, I'm not used to using this pen a lot. That's why it's very hard. Now I came down. So this will be 4, 2. Along with this, I will also have this also. Since this is a vector, right now this is 0, 0 here because I have entered the distance for 5 as well. This is again 1, 0. This is again 2, 0. This is again 3, 1. So this is for 4, this is for 5. 4, 5. Right now here we have 4, 2. Alright, so for 4, 2, I see. At this point my answer is 1. And at this point my answer is 0. But now I have entered, I've initialized another distance, 0, 0. Okay, I go up. Right now this is 3, 1, 3, 1 for 4, 5, but it's also 1, 0. I go down now, so 3, 1, sorry, 4, 2, 4, 2, and finally 2, 1. So this is another answer because 7 is the only leaf node that I have encountered. I mean, it's just encountered, so I don't have a distance for it. So 2, 1 is the distance from 6, and it's a valid answer. So answer will be 2. Finally, so this is the approach, the intuition. I don't know, it was a little to me, but the implementation is tougher for this one, I think. All right. So for this one, I need a vector called distances, we call it, or dist is fine. I won't initialize the numbers. I don't know how many leaf nodes are present in the tree. I traverse. This will be a in-order traversal. I'll have something called answer. I'll later define it. Uh, I'll pass the route. I'll pass the distance. I'll pass the distance. I'll have an answer. So I'll return answer here. This will keep track of the number of pairs. Okay. Now I will have a void traversal function which will contain arguments as key node, vector of distance, sorry dist, and this will be with reference, and this will be distance. Alright, if the root is null, I'll return. Otherwise, I will go through all the depths. See, at this point, I am going down, right? At this point, I'm going down to certain depth. So what we have to do when we go down, we have to increase both. By the way, this must be vector of vectors since we have two variables and two, or it can be a pair as well. But I'll use vector probably because I find this cleaner in terms of both first and second to you know to access the first and second variable of pairs is a little too uh, probably a big name for just a small access, I guess. So I is equal to I'm traversing through this vector, right? So I have to increase the depths and the downs, the first and the second uh, uh, elements, first and second elements. I'll have to increase, so I'll traverse the dist vector and increase the first element by one, second element by one, and I will call this is a level order traversal. Why we are doing level order, by the way? Because basically you want to process both the leaf nodes before you come to the parent node. So that can be done. Yeah, I mean, because basically what you are doing, you're going here, you're coming up, then you're going back down here. Right? That's what you're doing. And for that, I mean, I don't know if we can solve it other ways as well. I don't see problems here, but that'll be a different implementation. Root left, I go left. All right, I go right as well. I do something here. We'll do it. I go right. I pass the distance. At this point, I will check the answer. How will I check the answer? So if this root is a leaf node, if this node is a leaf node, which means if it's the left and right children are null, then I will traverse all the distance, all the dist elements, and I'll increase. Oh, sorry, I'll check if the dist I 0, so first element of dist is less than equal to distance, is it? If it is, then answer needs to be implemented. At this point, I'm backtracking, right? For the left node, I'm backtracking, I'm going up. So I'll have to do something which needs to take care of the down vector as well, right? So I'll traverse the this vector again. Here I'll check if the list of second element is greater than 0, then I'll have to reduce the first position and the second position of this. Else, I'll increase only the first position. Sorry, the first position as in 0. Okay, so this is good. I'll have the same backtrack function for the right part, after the right part as well, because I'm doing the same thing here. I'm coming up, so that's it. This is simple enough. And now at this point, I have checked. I've returned for fourth left child which does not exist, fourth right child which does not exist. So if left and right child does not exist, I'm here. Here I'll check if root left and root right is null. Then I add this. I'll add the first. I'll add the initialize the distance for this particular node, which is a leaf node. Now I'll return. So there's one thing missing here. I'll see. I'll try once if this works, and I'll update that. There must be some problems here. Traversal, traversal. That looks good. Mm, oh, yeah. Now let's see. Okay, this my bad. I guess then. Alright. So at this point, we think that this does not work. Right? We see that this does not work. Why it does not work? So at this point, why do I need something? I need to return something to identify that I don't need to update this. I can explain it with this example again. So at this point, what do I have? 3, 2, isn't it? I have 3, 2. Uh, this 3, 2 is coming from 4, from 5. I have not introduced 0, 0 as of now because I'm at this point where I'm going to the left side and I'm seeing that it's a null. I return back. So when I'm returning back, I'm essentially calling this function, isn't it? So if I'm calling this function will check that this is greater than 0. It is greater than 0 for certain depths, which is true, I guess, but I don't want to really increase it, right? Because I have not essentially returned back from anything. But technically, I have returned back, but I have not returned back because in practical example, there's nothing here, right? This was null. So at this point, if I don't check a call to this processing to this, if I don't have a check for these scenarios, then what will essentially happen is I'll return back, and at this point itself, at 6 itself, 3, 2 will become uh, probably 2, 1, and this will become 2, 1, which is wrong, which is incorrect. So essentially, when I'm returning back from here, I'll return something called false. This will be a return aspect, and return type will be bool, and I'll get something in A, or I'll call it is null. If it is null, then I don't need to adjust anything. Alright, I don't need to adjust anything. I'll do the same thing here, is null. Then please don't adjust anything. Let me just do this. This will be here. This will be here. Now I return true here because at this point I need to adjust things because this is not something. This is a node. This was a node at this point. It was not null. So alright, this should work. Let's see if it does. Uh, Open that. Opening this. Let's see what's wrong. Oh, I guess I need to increment the second element as well, not just the first element. It does work. The time complexity is a little tricky here because uh, because you see that we have a traversal of each and every node, so that's O of n. But in every traversal, we are checking the distance, and the max distance size will be equal to the number of leaf nodes. The number of leaf nodes is nothing but uh, the maximum number of leaf nodes can be something. Okay, this is somewhere around O of n square in that case, I believe. All right, thanks, guys.